Your next reading is sampling and estimation. These are the specific learning outcome statements, and these are the key areas that we will be covering in this reading. Inference about population from sample data, central limit theorem, calculation of confidence interval, and when to use Z statistic and when to use T statistic, and certain areas on sampling biases. So these are the specific key areas we'll be discussing. Okay, first learning outcome statement: define simple random sampling and a sampling distribution. First of all, what is simple random sampling, or basically what is a sample? Let's say we have a population, S&P 500 for example. We just select few stocks from this population so as we can draw some inference, some conclusion about the whole population. That's what you call sample. So what I select is sample, and from where I select the sample is the population. That's the whole universe. Okay. So what is the random sampling? Random sampling refers to a method of collecting a sample in which each and every element in S&P 500 has an equal chance of being included in the sample. Means every stock in S&P 500 has equal chances of being chosen. Right, so this is what you call random sampling. Every element in the population has equal chances of getting selected, getting chosen. Fine. Then what is sampling distribution? Sampling distribution refers to the distribution of sampling statistic. Like for example, so basically if we draw many samples from this population, all the possible outcomes of the samples, then we calculate the sample mean for this sample, sample mean for this, sample mean for this, and sample mean for this. So when you construct a distribution of all these samples mean, this is called sampling distribution. All the possible outcomes of sample means, which you call the sample statistic, of equally sized. Let's say our selection size is 50. This sample has 50 elements in it, 50, 50. So constructing a distribution this way of sample means is called sampling distribution. Right? So we may take maybe 10 such samples of 50 each, or maybe you can go up to 20 or 30, as many as you want. So we'll do it repeatedly. That's why it's called an iterative process. Sample statistics from multiple samples, and it's an iterative process. We will keep on doing it. By repeating the process several times, we will end up with several different estimates of sample mean, and then arranging these sample means into proper suitable representation is what you call the sample distribution. That's what we've discussed in our previous reading. So one important condition here is that all the sample population, they should have same sample size, 50, 50, 50, 50. That's an important point to be remembered. All right. Equal sized samples. And then creating a distribution of these sample statistics is what you call the sampling distribution. All right. Next learning outcome statement says, explain sampling error. What is sampling error? Sampling error is basically the difference between the sample statistic and the quantity it is intending to estimate. Like for example, we want to measure the mean return of S&P 500, right? How close is this sample mean or sample statistic with the population mean? Or in other words, the difference between the sample statistic and the population parameter. This is what you call the sampling error. The difference between the sampling mean and the population mean in our example. This is called sample error. Now, what causes this error? Why not the mean of my sample is equal to the overall mean of S&P 500? What's the reason? There are two reasons. First is called sampling error. Means that I may not have selected suitable sample and the sample that I've selected, they are basically not representative of the population. Incorrect selection of samples. My samples are not representative of the population as a whole. This is the first error. This is called the sampling error. Other is called the non-sampling error. Non-sampling error means maybe I'm a bit biased. I missed by maybe I've just focused on a particular aspects of S&P 500. So this could cause sampling error. So the important point here is to draw as many samples as possible. Larger the sample size, randomly selected, the more representative would it be for the whole population. So in order to get a representative sample, the sample must be drawn randomly and it should include the whole population. Okay. Now, next learning outcome statement says distinguish between simple random and stratified random sampling. We have discussed simple random sampling. It's simply selecting samples randomly from the population where each member or each element has equal opportunity of being selected, equal opportunity or equal probability of being picked. This is called simple random sampling. Now, the problem is that what if the population might contain stocks or whatever the population contains, they might be so different. There is quite a contrast in the elements within the population. So then in this case, the simple random sampling would be unreliable. The conclusion that we might draw would be unreliable. Then what we do? Then the solution of this problem is that we can stratify or we can subdivide our population into stratas. Like this is the population now segregated into 3 stratas or 3 stratums, 3 parts. I will explain with the help of an example. Now the elements within part of the sample, they are identical. Here we have similar and here. Now this population has been divided into 3 categories, 3 stratums. Now collectively they are called strata. So we have basically subdivided the population into separate groups, and each group here or each stratum here is composed of elements that have common characteristics or common attributes. As you can see, they look similar, and these attributes distinguish them from the other stratum or other stratas, right? So this is what you call now what we are going to do, once we have split the population into these different stratas, then we will select samples from each stratum. Right? Now, how many number of members would you select from each stratum depends upon its relative strength in the whole population. Let's take an example to explain the idea. This is already explained, all these terms. Equal probability of selection, that's random sampling, subdivision of population strata, and common attribute discussed. And then we combine these samples for our final selection. All right, this is a good example here. Let's say we have divided our population into 3 stratums. Suppose we want to estimate the mean return on 1000 stock in a country, but 300 small cap, 500 mid cap, and 200 large cap stocks. So let's say here we have 300 small cap, 500 mid cap, and 200 large cap. Now we want to select a sample of size, let's say 40. Right? Now, how many should we select from this stratum? How many from this? How many this? Let me show you. From here we will select, we need to select 40. So how many should we select? There are total 1000, remember. So it's going to be 300 upon 1000 multiplied by the sample size 40. So when you simplify, it means you should select 12 from this population, then 500 upon 1000 multiplied by 40. When you simplify, you need to select 20 from this, and finally from here you will have 200 out of 1000 multiplied by 40. So when you simplify, your result should be the balance, of course. So that will be 8. Now this will give you a total of 40, right? Where we have selected certain numbers from each stratum. This is what you call the stratified sampling. All right, next LOS. Distinguish between time series and cross-sectional data. Now, this is the table that will bring out the difference between these two. When we say time series data, I'm sure you would have studied in your undergraduate courses. Time series, we plot time on the x-axis and certain variable on the y-axis, and then we see how things move. Something similar. So time series data means the observations made over a period of time at regular intervals. Over a period of time. The time could be a day, a stock price on every day, or a stock price every week, or a stock price every month, or a stock price every year. Single stock. Observation of a single stock. Right? Daily closing prices of a single stock. That's called time series data. And cross-sectional data, on the other hand, contains observations on multiple phenomena, like closing prices of 100 stocks at the end of the year or at any point in time. Gentlemen, I always emphasize that you should pay specific attention to the command word, also called the action verb. As long as you are able to justify your preparation with the command words, it means you are well prepared. Just distinguish. No computation is needed. Just we need to be able to distinguish between time series and cross-sectional. So action verb, or what you call the command words, are very essential. All right, next LOS is a very important one. Explain the central limit theorem and its importance. Central limit theorem, basically, let's take an example. This is your population with the mean mu and variance sigma square. We select a sample with mean x and a certain variance. Now, if your sample size is large, enough, the sampling distribution that you will construct will tend to assume a normal distribution. Right? When the sample size is sufficiently large, the sampling distribution will tend to become a normal distribution. So this theorem can be extended to any distribution, so that when n increases, that's the number of samples increases, the distribution becomes almost normal regardless of its shape. So this tool, basically the central limit theorem, the basic idea behind this theorem is that when the number of samples increase, then the sampling distribution will tend to become a normal distribution, almost normal distribution. So a very useful tool, especially when we will be constructing confidence interval just after a few slides, or especially when testing hypothesis. That's your next reading. Testing hypothesis, one-tailed test, two-tailed test. This is your level of significance. So whether the test statistics fall within the critical region or not. So that testing of hypothesis, this is highly valuable for testing of hypothesis, the central limit theorem. We can convert distributions into normal distribution, and then we can apply the testing of hypothesis concepts there. So this is an important point. As long as n is sufficiently large, any non-normal distribution can be approximated as normal, and then we can apply z-table there. Now the question is, what do you regard as a large n? So anything that is greater than or equal to 30, when the number of sample size is at least 30 or above, so such a distribution can be approximated as a normal distribution. So that was an important point, right? It's a useful tool, and large n, as I said, it should be at least 30 or above. So this explains central limit theorem, just an overview, then we will do the questions shortly. So as I have repeatedly been saying that the outline, the overviews, they covered hardly 10 to 20%. The actual understanding comes from the question. So these are just the ideas, and we apply these ideas on actual questions. That's what refines your understanding, right? That's the key in professional certification, being able to solve the questions. Okay, next, a very important learning outcome statement. Calculate and interpret the standard error of the sample mean. Now, what is the standard error of sample mean? Standard error of sample means basically is the standard deviation of the distribution of the sample means. We have many samples, this. As you remember, we did it repeatedly to develop a sampling distribution. So the standard deviation of the means, let's say if we are trying to estimate the mean, the variation, the standard deviation of the means as given by these samples is what you call the standard error. Now there is a very important distinction. We may have a single sample, S1 for example, and there are many, let's say 30 values in this, 1, 2, 3, 4, 5, 6, 7, so on. Standard deviation alone of this sample, it measures the variability within a single sample. Standard deviation of single sample means how varied are the selected samples from each other. I'm sure you know what standard deviation, we did it in our previous learning outcome statements, previous readings. But when you say standard error, then basically it is the deviations between the samples, many samples. Standard deviation of single sample measures the deviations of the elements within the sample, but the standard error measures the deviations of many samples. That's the distinction you must remember, right? Standard error gives an estimate of the variability between many samples, right? That's the idea. All right, now this is the formula we use to calculate the standard error. But remember, an important point to be noted here, this will be used when we have the population standard deviation. Provided the population standard deviation sigma is known, the standard error of the sample mean can be calculated using this formula. But in most of the cases, you will not have the standard deviation of the whole population. Maybe your population consists of thousands of elements, huge population. So in that case, what if we do not have the population standard deviation? In that case, we have an alternative formula. When sigma for the population, the standard deviation of population is unknown, the standard error of the sample mean can also be calculated using the standard deviation of the population divided by the square root of the sample size. The same denominator is the same, but here we have the population standard deviation, but here we have the sample standard deviation, right? That's an important point. All right. Now the question is, why standard error is so important? Why are we interested in it? We need to know. Standard error, basically it gives analysts us an idea of how precisely the sample mean estimates the population mean, because we are trying to get an inference, draw conclusion about the population by calculating the sample mean. Based upon this, we want to draw a conclusion about the sample mean, right? That's what we want to do. So the standard error, basically it shows you how precisely the sample mean estimates the population mean, right? So whatever the result of these two formulas give you, whether you use this formula ideally, but most of the cases you will use this one. If you get a lower value, if the result is lower, what does it tell us? The low value of the standard error indicates that you have made a precise estimation of the population mean. And conversely speaking, if the number is larger, that indicates that the precision is less. The estimate is not as accurate as it should be. Okay, let's try to apply this on a question so as we can make a better understanding. Here is it. It is, in a certain property investment company with international presence, workers have a mean hourly wage of $12. Okay. With the population standard deviation, now this is important. We have been given the population standard deviation, that is $3. And given then the sample size is n, that is 30, estimate and interpret the standard error of the sample mean. We have to estimate and then also give our interpretation. So in this case, since we have been given the population standard deviation, so in that case, we will apply this formula. Standard error of mean is equal to the population standard deviation. Let me write down the formula first so you know what I'm doing. Now plug in the numbers. $3 divided by the square root of 30. And when you will simplify this, you will get 0.55. Now what this 0.55 tells us? This 0.55 tells us that this could be the level of precision in our computation of the population mean, because we did not conduct an investigation of the whole population. We just taken out 30 samples. Based upon this, we are trying to draw our conclusion. So this number tells us that this is the level of precision in our computation, right? We can assume that the precision level is $0.55. The higher this number, it means less precise it is. If this number is smaller, it means it is more precise. Or in other words, we can give it this way. This means that if we were to take many samples of 30, 30, 30, 30, 30, 30, we would get a distribution with an expected mean of 12, and standard deviation of 3, the standard error would be 0.55. That's the basic idea. Smaller, the better, the more precise is the estimation. Larger means less precise. Now let's do another question to enhance our understanding. Suppose a sample contains 30 monthly returns of McReady Incorporated. The mean return is 2%. And the sample standard deviation. Now in this case, we have been given the sample standard deviation, right? Calculate and interpret the standard error of the sample mean. So we can't use this now. We can't use because we have not been given the population standard deviation. So what we should do now, we have an alternative. We can use this. So we have been given the standard deviation 20. Sample standard deviation, and we have been given the sample size 30. Now if you simplify this, you will either get a result in decimals if you change the percentage sign, or if you don't, you will get 3.6%. Now, we have calculated it now, but we need to interpret it as well. What does the number tell us? This number tells us that if we took all possible samples of 30 from this population, and if we prepared a sampling distribution of the means, the mean would be 2%, and the standard error will be 3.6%. The same conclusion we drew previously in dollars, but here we have in percentages, because previously the numbers were in dollars, but here it's in percentages. And as I said, the smaller the better. Okay, one more question. As I said, questions is what you need more to refine your understanding. The mean hourly wage for Iowa farm worker is 13.5. Okay. With the population standard deviation 2.9, that is good. We have been given the population standard deviation $2.9. Calculate and interpret the standard error of sample mean for the sample size of 30. That's exactly what we need. We needed these two things. Now we have them. Standard error of the sample mean is equal to the population standard deviation divided by the square root of the sample. So it's going to be $2.9 divided by 30. And it gives you result now in $0.53. The conclusion stays the same. This means if we were to take many samples of size 30 from the Iowa farm worker population, that's our whole population from where we're selecting, and we prepare a sampling distribution of the sample means, we would get a distribution with expected mean of $13.5 and a standard error of 0.53. Right? That's what the interpretation is. All right, now moving on to our next learning outcome statement. It says, identify and describe desirable properties of an estimator. Okay, first we need to know what is an estimator. What is a point estimator? Just like we were discussing, we use sampling, we drew out a sampling mean, and based upon the sampling mean, we just want to draw some inference, some conclusion about the whole population. So basically, the point estimator, PE, is a sample statistic. Most of the time, it's mean. Is a sampling statistics, mean in our case, and it is used to estimate the unknown population parameter. We want to use our sample statistics mean to estimate the mean of the whole population. So this sample statistic, the mean in case, is our point estimator. Simple. So what we have as a tool to get an inference about the whole population is the point estimator or sample statistic. Right? So remember, this point estimator, it's a random variable. It could vary from one sample to another. We may have drawn many samples, so our mean may vary between these different samples, and this variability of means in these samples is what we measure by standard error. That's what we discussed earlier. Right? Now there are three important desirable properties of an estimator. Let us discuss these one by one. These have all been discussed. Desirable properties of an estimator. First, it must be unbiased. Your point estimator must be unbiased. What does it mean by being unbiased? Bias means the difference between your point estimator and the value that you want to estimate. This gap should be as close to zero as possible. This is your sample statistic. This is the population parameter. This is the sample mean. This is the population mean. And we just want this difference to be as little as possible. Should be zero ideally. If it is, then we can say the point estimator is unbiased because it is close to what the population mean is. All right. Next desirable property is efficiency. point estimator should have more efficiency. What does the word efficiency means here? Let's say if we have two unbiased estimators, point estimators, we would prefer the one with small variance, right? Let's say this one has a larger variance than this one. So we would prefer that point estimator with smaller variance, because this means it's more precise in statistical terms. So we need less variability in our point estimate. More variability means that it will give us imprecise results. That's the third desirable feature. Then the second one, now this is the third one, consistency. Now this is an interesting property. If your point estimator is consistent, as you keep on increasing the size of the sample, then the probability of finding the actual parameters would approach to 100%. Now let's say you're talking about S&P 500, and initially you took a sample size of 50. If you keep on increasing, it's quite a common sense. If you keep on increasing the sample size from let's say 140, you take up to 200, or if it's up to 500, and you're taking the whole population. So if the price estimator, if the point estimator increases, the probability that the estimator will cover the entire population will be 100%. Just a common sense, but this is one of the statistical importance we need to discuss. So this is the third property of point estimator. Or let's do a few questions again to enhance our understanding. A simple random sample is a sample drawn in such a way that each member of the population has some chance of being selected in the sample. Same would have been correct, but not some. Each member of the population has an equal chance of being included in the sample. Now that's what you call simple random sampling. Each member of the population has equal chance, equal probability of getting selected. B makes perfect sense. Should we move on, or let's read C as well? A 1% chance of being included in the sample. We can't specify this probability this way, so this is incorrect. So that makes B to be our correct option. All right, next. The sampling distribution, the distribution drawn from many sample means or sample statistics. A sampling distribution of a statistic is the probability distribution made up of all possible what? All possible observations from the underlying population. That's the samples, not the sampling distribution. Wrong. All possible sample statistics computed from samples of varying sizes. Now this is something that will help us cancel this option immediately. No. In sampling distribution, we have agreed in our very first LOS, the sample size should be the same. This is not. If the sample size has been set 50, every sample is 50, 50, 50. You can't vary the size of the sample. This is wrong. So then it has to be C then. Sample statistics computed from samples of the same size drawn from the same population. Perfect. This is the perfect option. C is the right answer. All right, next. Sampling error, we just discussed a little while ago. Sampling error is defined as what? Sampling error is an error that occurs when sample of less than 30 elements is drawn. Wrong. This is not an error. You can have less samples, you can have more than 30, less than 30. So this is not the sampling error. It's an error that occurs during collection, recording, and tabulation. Wrong. Sampling error basically is the difference between the value of a sample statistic, sample mean in our case, and the value of the corresponding population parameter. That is sampling error. So that makes C to be the correct option. All right, now this is a good example. The mean age of all CFA candidates is 28 years. The mean age of a random sample of 100 candidates, because there are thousands and thousands of CFA candidates. We can't ask dates, their age, everyone. Is not possible. It's not possible to ask every CFA candidate and then enter the numbers in our calculation. So we just selected a random sample of 100 candidates and we found out the age to be 26.5. Now this is what will help you to understand that. Now this difference between the sample mean and the population mean, this difference is 1.5. Now what this is called? This is called sampling error. The gap between your sample statistic and the population parameter is what you call sampling error. All right. Next. Now we have sample of debt to equity of 25 publicly traded US banks as of the fiscal year end 2003. It's an example of what? We have debt to equity ratios of 25 banks in the US at the end of 2003. Let us recall, what did we study a little while ago? When you have multiple phenomena, 25 publicly traded banks, and some important measurement about them on a particular point in time, this is called cross-sectional data. Time series data means that we would have selected a single bank, let's say ABC Incorporated, and we would have noted its debt to equity ratio at the end of every year over a certain period of time, or the end of every month for a particular year. That would have mean it's a time series. So this is basically a cross-sectional data. Without looking for any further, that makes B to be our correct option. Next, to apply the central limit theorem to the sampling distribution of the sample mean, the sample is usually considered to be large if n is greater than 30 or more. Then we can approximate the distribution to a normal distribution. Seventh, if n is large and population standard deviation is unknown, we don't have population standard deviation, n is large, the standard error of the sampling distribution of the sample mean then can be calculated this way. Right? We can simply use the standard deviation of the population divided by the square root of the sample size that we've just done. So let us see which of these options contain the formula. The sample standard deviation divided by the sample size apparently looks correct, but basically it's the square root of the sample size, not just by the sample size. So that is basically incorrect. B, the population standard deviation, we can't use this because we don't have population standard deviation. B is incorrect as well. What about C? The sample standard deviation, yes, divided by the square root of the sample size. So this is quite a straightforward question, but that at least reinforced the idea on your head. C. Okay, the standard error of the sampling distribution of a sample mean for a sample size n drawn from a population with a mean mu and a standard deviation sigma. Now that's fairly straightforward. We need a sample standard error of the sample when we have been given the standard deviation of the whole population divided by the square root of this. This is we've just done a little while ago. So this would mean population standard deviation divided by the square root of the sample size. That is C. He's emphasizing upon this because this is the basis of your next readings where you'll be calculating the confidence intervals. All right, next. Assume that a population has a mean of 14, okay, and a standard deviation of 2. If a random sample of 49 observations, that is n, is drawn from this population, the standard error of the sample mean would be, standard error of sample mean is equal to the standard deviation of the samples divided by the square root of the sample size. So S is given as 2 and n is given as 49. So it's going to be 2 by 7, which if simplified should give you 0.2857. Right? Straightforward. Okay, then the population mean is 30. The mean of the sample size is 100. Or 100 sample size is n 100. And this is the sample mean. The variance of the sample is 25. The standard error of the sample mean. Now, we need to calculate, have we been given the population standard deviation? No. Then we have to apply the formula. (30) and sample mean, okay. S divided by n. We have been given population mean. We have been given the mean of the sample. We have been given the variance of the sample, that is 25. So it's a sample variance. So since it's 25, that is s squared. Since we need the standard deviation, so you need to take the square root of 25. So that's going to be 5. And how many samples are there? The sample size is 100 in the square root. So it's going to be 5 by 10, and that's 0.5. So you look for this. This is variance, not the standard deviation of sample. So you need to take the square root. So that gives you 0.5. Next, which of the following is least likely a desirable property of an estimator? Efficiency was there, consistency was there, but reliability, it was not one of the desirable properties. This is wrong, and hence this is the right answer. Alright, so next learning outcome statement says, describe the properties of students' t distribution and calculate and interpret its degree of freedom. This is the next LOS, an important one, of course. What is students' t distribution? Whatever we have learned so far at this point in time is just z distribution for normal distribution, z tables. What is t distribution? What is t distribution? T distribution basically is also a bell-shaped probability distribution which is symmetrical about mean, like this is the normal distribution, right? So t distribution is also bell-shaped, but the difference between the t distribution and z distribution is that t distribution has fatter tails. It is symmetrical, yes, but it has fatter tails, as you can see here. Okay, so the question for us is that when t distribution is considered best to be used in certain situations. First, when we have small sample sizes, if you remember in a previous example, when n is greater than 30, central limit theorem, we can literally use normal distribution to solve any type of distribution if n is greater than 30. And there are other some important points to be discussed. We'll go along with these as we move forward. So t distribution is suitable when the sample size is less than 30. And this is important. The population variance is unknown. If the population variance is unknown, we use t distribution. We'll explain as we go along through questions. Sample size is less than 30, we use t distribution, right? So we can use t distribution to get our numbers, our results. Let's see how does it work. How do we calculate the t-score? You remember from your previous learning, z-score is calculated by the observed value minus mean upon standard deviation. But here the t-statistic is calculated using this formula. Now what this formula tells you, that this is the sample mean. I hope I have these numbers. Yes. X here represents the sample mean which we have been discussing so far. This is the population mean. Since we do not have the population standard deviation, if you remember right here in the second or third point, we do not have the population variance or standard deviations, then in this case we have S, that is the standard deviation of the population. So that's exactly what it says. S is the sample standard deviation and N is the sample size. So we can use T statistics to solve such a problem, right? So this is just simply, so how does it work? What exactly do we need to use T distribution? Let us take a question and then try to apply this and get our results. Here is an important term called degree of freedom, n-1 degree of freedom. The ratio of T sample mean minus the population mean upon the standard error of mean. It follows a T distribution with mean as 0 and degree of freedom n-1. If you remember the normal distribution, 0 mean, and this was the variance, right? But here the mean is 0, but we raise it to n-1 degree of freedom. Let me explain this, what basically is degree of freedom. Let's take an example. Let's say I have A, B, C, D, and E. 5 alphabets. I select one out of them, that's A. Gone. I have to select another one from these. I select C. I need to select another one. I go for D. I select another one, B. But basically when I have to select E, I have no freedom at all. I have utilized my freedom in selecting these 4 numbers, these 4 alphabets. So basically if the sample size is 5, my degree of freedom is 5 minus 1, that is 4. Right? So the degree of freedom basically is the number of degree of freedom refers to the number of independent observations. The total observations, 5 minus 1. If you have 12 observations, your degree of freedom will be 12 minus 1, 11. If you have 25 observations, your degree of freedom is 25 minus 1, that is 24. That's what you mean by degree of freedom. Let's say if you have 10 observations, and if you're analyzing those observations, so degree of freedom is just 9, because the 10th one is just, there is no freedom for you for the last one. That's an important point to be noted, because this will be used. Okay, so this is how your T distribution looks like. This is the original one here, with the degree of freedom is 1. You have a T distribution represented by this lowest bell curve. When the degree of freedom becomes 4, it tends to become more peaked. When degree of freedom is 15, as the degree of freedom is increasing, the distribution tends to be more narrower, more peaked. All right, now let us discuss these notations one by one. But before we do that, let me show you what exactly do we mean by. If you remember from your previous studies, this is what you call the degree of confidence. 90% if the degree of confidence, the level of significance is 10%. That is 100 minus 90. Level of significance is called as alpha. And then degree of confidence is 1 minus alpha. Right? Degree of confidence, if 95%, then means the level of significance is 5%. And likewise, at degree of confidence 99, the level of significance is 1%. This is similarly what we have applied in our normal distribution. That's same applicable in case of T distribution. So we are looking for T alpha, just like in our normal distribution. The critical values in a two-tailed test, you will discuss and study these in your hypothesis testing in the next reading. So this is what you call the level of, let's say if you're talking about 10%, then it will be split into 2 parts, 5%, 5% here. Level of significance. Talking about 5%, then it's going to be 2.5% here and 2.5% here. If it's 1%, it's going to be 0.5% here and 0.5% to the left tail. That's the Same thing is applicable on T alpha as well, that we have discussed in our normal distribution in our previous learning. And as we have also discussed in the normal distribution, that the distribution is symmetrical, 1/2. Basically, they are the mirror images of each other. So whatever you have here, you have the mirror image here. Similarly, that's T alpha minus T alpha is basically equal to T1 minus alpha, because they are totally opposite to each other with a fatter tail here. Right? So T alpha is minus T1 minus alpha. So this region, they will be the same because the distribution is symmetrical. Okay, let us apply this in some meaningful way. Let us apply this in some meaningful way. So how do we interpret the confidence interval? That's, I think, the next part of the LOS. We have basically discussed T distribution. Now we would like to interpret the degree of freedom as well as the application of confidence interval. Okay, how do we interpret a confidence interval? Let's say 95%. What does it mean basically? When we say a confidence interval of 95%, just in the next slide I'll show you. The level of significance would be 5%. Right? Keeping that in mind, 95% and 5%, let's read what it says here. If we construct a similar interval using samples of equal sizes from the same population, 95% of the interval would contain the true value of the population parameter, and 5% chances are that it will not. Right? So when you say 95% of confidence interval, it means that 95% of the interval would contain the true parameter right here, just 5% would not. 2.5 in the lower tail and 2.5 in the right tail. That's what you mean. We'll refine the idea as we go along. Doing questions will enhance the further concepts. So how do we construct a confidence interval? To construct a confidence interval, first of all, you will have to come up with a point estimate. What is a point estimate? That will help us to draw conclusion about the whole population. Right? So this is the formula we'll use. The point estimate, that's our sample statistic. To this, either we will add or deduct a reliability factor. What is, we'll discuss. 1 standard deviation from the mean, 2, 3, and so on. We'll discuss this. And the standard error, that's what we have already calculated. Right? That could either be this if the population standard deviation is given, or if the sample standard deviation is given this. So this is how we calculate the confidence interval. Point estimate plus minus reliability factor into standard error. Now let us do some computations and then try to interpret what exactly does it mean. But I think your next LOS asks you to see it from 3 parts. Calculate and interpret confidence interval. This is the LOS we are doing. For population mean, given a normal distribution with known population variance. First case, scenario 1. An unknown population variance, the second, and an unknown population variance and a large sample size. These are the 3 specific conditions given to you in which we will have to determine the confidence interval. There are some questions coming our way, and that will explain the idea further. So I hope you remember this was discussed in our previous reading, that 90%, I hope I don't need to spend time here. This is already covered in our previous reading. Let us go into the practicality of this. Let us discuss the first scenario where the population variance is known. How do we calculate the confidence interval? When we have the known population variance, we use this formula to calculate the confidence interval. What are these legends here mean? This X here is the point estimate, our test statistic. This here represents your Z-score. We'll do it shortly. And this is the standard error. we calculated in our previous. So I hope you remember this table from our previous reading. And the degree of confidence 90%, the level of significance 10%. So that is one standard deviation. If 10% is the level of significance, we are basically 1.645 times away from the mean. When the level of significance is 5%, normally we used to say it's 2, but it is basically 1.96 standard deviation away from the mean. And if the level of significance is 1%, we are 2.575 standard deviation away from the mean. This is exactly what we discussed in our previous reading. So let us try to correlate and apply this in few situations. So the second situation, this one, when the population variance is unknown. Normal distribution with unknown variances. If you remember previously, why did we study t-distribution? Because t-distribution involved when there was no population variance. It is suitable when, let's see here, unknown population variance. It is useful when this population variance is unknown. Now, that's the condition, the second one where we will apply the t-distribution. We will do all these with numbers that will enhance your understanding. Here it is. When the variance is unknown, we construct the confidence interval for the mean by replacing z-score in the first scenario with the t-score. How do we calculate? All is coming. Just wait for a few moments. Right? Similarly, we will replace the sigma with s. So if you just compare these two, you will see that they are almost the same. Just that it has been replaced with t and it has been replaced with the population standard deviation. That's exactly right here. So this is your point estimator here. And this is the t-distribution use we'll see. And then here we have used the standard deviation of the sample. Right? How it is used, all is coming. Just have patience. We'll discuss. And the third one. When the population variance is unknown, but the sample size is large. If you remember the central limit theorem, that theorem said that if the sample size is greater than 30, any known normal distribution can be approximated as normal distribution. And we can use the normal distribution to calculate our results, right? And thanks to the central limit theorem, we can approximate about any type of non-normal distribution if our sample size is at least 30 or above, right? So we, again, in this case, will use z-score. So you will be given questions, but then you will have to interpret which of the situations the question fall in and you will solve it accordingly. So let us just quickly rush to the questions to enhance our understanding in all these three cases. How do we calculate the confidence interval? So reading theory would not be sufficient unless you do the questions. All right, so this is a straight summary. What we have done so far in this reading. If your distribution is normal and the variance is known, when you say variance is known, that is the population variance. You will use z statistics whether the sample size is less than 30 or greater than 30. That's for sure. If it's a normal distribution, the sample size doesn't matter. You use z statistics in case of sample size less than 30, more than 30. All right. Now, if the distribution is normal, but the population variance is unknown, in that case, small sample size, you will use t statistic, less than 30. We discussed that a little while ago. And if the sample size is large enough, we have the option to either use t statistic. We can also use z statistic. Here is asterisk sign, means the z statistic is theoretically acceptable here, but use of t statistics is more conservative, give you more conservative results, right? So what if the distribution is non-normal, and in one case the population variance is known, other it is unknown? Here the central limit theorem comes in action. Non-normal distribution, but the population variance is known, then we use, in this is the case, we use z statistic. And when it's a non-normal distribution, the variance is unknown, then we use t statistics even the sample size is large. But here again we can use z statistics, just we discussed a little while ago, that it can be used if the sample size is greater than 30. Now all this maybe covers 10 to 15% of our understanding. The actual understanding will come from the questions. Now let us do the questions and then refine our understanding what we have done regarding confidence interval. Consider a practice exam that was administered to 36 level 1 candidates. Okay, so what it tells me that this is n, sample size. The mean score on this practice exam was 80. Okay, assuming a population standard deviation is equal to 15. Construct and interpret 99% confidence interval for the mean score on the practice exam for 36 candidates. Note that in this example, the population standard deviation is known. Right? We have it here. Population standard deviation is 15. So we don't have to estimate it. It's already there. Now, we know the formula that we need our sample statistic, which is given here. Since it's normal distribution, we have the standard deviation of the population, so we will use here Z alpha. Since our level of significance, our degree of confidence 99, so it's going to be alpha by 2, that is 1% by 2. Let me write it directly. Alpha here is 1%. So 1 upon 2, that gives you 0.5% or 0.005. Right? We will simply write alpha by 2. Right? Multiplied by the standard error, that is standard deviation of the population divided by the sample size. This is how you will calculate your confidence interval. All right. Now, what is the mean score on the sample? That is 80. Plug in 80 plus minus. Since we are talking about level of significance of 1%, which means, and you know that, it is 2 point, let me take you back, what do I mean here? It is a 2.575. Z alpha by 2 here is 2.575 times of mean from the standard, of the standard deviation from the mean. So it's 2.575. So we just need to replace this there. We don't need to consult the Z table here. We just need to plug in the numbers here. So it's 2.575 multiplied by the population standard deviation is given here as 15 and divided by the square root of the sample size. It's now the simple arithmetic. When you will simplify, you will get 80 plus minus 6.45. Right? And when you simplify this, what you get is a maximum of 86.45% and a minimum of 73.55. Now, if 99% is the degree of confidence, then it means your true population parameter will fall within this. 99% confidence interval ranges from 73.55% to 86.45. Or if this is the score, you can remove the percentage sign. This is the value, the lower and the upper. So you are 99% confident that your true population parameter falls within this range. Okay, we got some basic understanding. Let us go ahead for a bigger question. Annual return on energy stocks are approximately normally distributed with a mean of 9% and a standard deviation of 6%. Okay. Construct a 90% confidence interval for the annual return of a randomly selected energy stock and a 90% confidence interval for the mean of the annual returns for a sample of 12. So we have to calculate the confidence interval for the single observation from the mean as well as the confidence interval for the population as a whole. Right. So let us first take out the numbers. So this is our test statistic 9%, the point estimator. Plus minus, since it's normally distributed and you're talking about 90% confidence interval, it means the significance level alpha is 10%. So Z alpha by 2, I'm sure you know it's 1.645 standard deviation away from the mean. So it's going to be 1.645 multiplied by, remember we need two things. First we need the confidence interval for a single observation, right? 9% plus minus 1.645 multiplied by 6% standard deviation. When you will simplify, you will get your result in the range 18.87% and negative 0.87%. So this is the 90% confidence interval range for a single observation from the sample mean. If you take the population as a whole, then you use the full formula. What was the full formula? You use the point estimator plus minus 1.645 multiplied by the standard deviation. What was missing here? The sample size. Now if you simplify, your range will be 6.15% to 11.85%. So at 90% confidence interval, this is the range for the population mean to be. That means the true parameter will fall within this range, and we are 90% confident about this. This was for a single observation from the sample. This was for the population as a whole. All right, moving on to the next question, and it is in continuation to the previous question. Let's return to McCready incorporated example. Recall that what we took, same information. We don't need to go back. All what we need is given here already. Recall that we took a sample of the past 30 monthly random stock returns. So this basically is N. And determined that the mean return was 2%. Okay. And the sample standard deviation, see, the sample standard deviation was 20%. We have been given the sample standard deviation. N is 30. Now what we do? Go back and see what situation do we fall in. We do not have the population variance, right? And N is 30. So you can do these with t statistics. Let us do with t statistics. Even we can do it with z statistics. N is equal to 30 or above 30. But let's do it with t statistics. When you apply t statistics, when the sample size is ideally less and the population variance is unknown, let us now apply t statistic. Okay. Since the population variance is unknown, the standard error of the sample mean was estimated to be, this is 3.6 already given, right? This is how we calculate standard error, sample variance upon the square root of the sample size. So this is what you call the standard error when the population mean is missing. Now the main question is given here. Now let us construct a 95% confidence interval for the mean monthly return. Since we are going to use t-distribution, we need some important things before we go on. We need to first determine the level of significance. Since we are talking about 95%, so it means t alpha by 2 is going to be 5% by 2, so that's going to be t 2.5 or 0.025, right? And remember, we need n minus 1, which is the degree of freedom. And how do we calculate? Simply take the sample size, that is 30, 30 minus 1, that is 29. So degree of freedom is 29. This is how you write t statistic. T 0.025 alpha by 2, that is the level of significance, and 29 represents the degree of freedom. No science, it's no difficulty. Just go to the t table given at the end of your every book, more specifically the one that carries statistic stuff. Here it is now. T 0.025 right here at 29. I hope I have it here. See, if you take one tail, that is 0.025, or two tails will be combined 5. So you can just see 2's half, 1's half, 5's half, 2's half, 1's half. So all this would represent the single tail. Down is simply the two tails. So what you're looking for, is t.0025025. At 29, it is 2.045. That's exactly what we needed. Now we apply the formula. The sample statistic here is 2%, right here given. Mean 2%, the point estimator. Plus minus T alpha by 2, that is 0.025 at degree of freedom 29. We calculated this, or we just saw this number in the table, 2.045. And multiply this with the standard deviation of the population, that is 20%, and divide it with the square root of the sample size, that is 30, right? When you'll simplify this, I'm going to write the straight result. It's going to be 2 plus minus 7.4%. So the final version would be 2 plus 7, that is 9.4%. And 2 minus 7.4, that is negative 5.4%. And I know you know how to do the interpretation, that we are 95% confident that the population mean would fall between these two values. The true population parameter will fall between these two values. Let's enhance our concept through further questions, but let's just read about some further LOSs. There are questions coming after these LOSs. Okay, next is describe the issues regarding the selection of appropriate sample size. Data mining bias, what it is. Sample selection bias, survivorship bias, look ahead bias, and time period biases. We need to know, describe what they are, right, with regard to sample. Let us discuss these one by one. First of all, we know, and we in our very earlier learning outcome statements, we concluded that larger the sample size, the closer you get to the 100% probability. That was just the LOS. So in general, larger samples are preferred to smaller ones. Why? Because when you have larger sample size, you will have more confidence interval, more reliability. And moreover, the most important one, if you remember, the standard error is equal to whether you use the population standard deviation or the sample standard deviation. In both cases, it is divided by, these are two separate formulas, by the square of the sample size. So look at this. If you have a larger sample size, so having a larger sample size will increase your denominator, which eventually will decrease your standard error, and that is good for us because standard error should be as less as possible. More precise results can be obtained. So this tells us that the sample size should be large, ideally, but there, of course, there are reasons why we don't have large sample sizes. There are costs involved, but having a larger sample size will result in less standard error, so more precise results, right? So this is what I think is covered here. When we have a larger sample size, we have more confidence and reliability because the standard error is inversely proportional to the sample size. I showed you using the formula. But why don't we have large sample size? There are certain reasons. Why large sample size are not used? Why there are certain reasons. First, the foremost must be that the cost is high. When the larger sample size is taken, the cost of computations, cost of gathering the data, it would be high. And second, this would be the first priority because the cost of sampling would go up. And the second drawback is that you might mix old data with the recent one, so this could result in outdated population parameter. Okay, so the first part is done. Then we have data mining bias. What is data mining? The data mining idea was originated in a chain of stores in the US. I hope you would have heard the name Walmart. That's where the data mining was originally developed. You will discuss data mining somewhat in your fintech reading, finance and technologies combination. So data mining basically, in simple words, it involves analyzing your historical data to develop some correlations, to develop some relationship between variables. The classic example given for data mining is that when it was studied in the Walmart, it was noticed that certain individuals, when they come back from home, they used to purchase 2 or 3 things together: a pack of cigarette, beer, and diapers. And you would know why. So when you get back from work, your wife would call you to bring diapers for the baby. And when you buy diapers, you most probably be tempted to purchase cigarettes and beer. So what Walmart did, when they realized that these 3 things are correlated, they are purchased simultaneously as per the past sales record. So they try to place these 3 items close so that more individuals come and they find these 3 things closer, so don't have to rush here and there for these 3 things. So this is how they develop the relationship. So data mining bias, sometimes we might arrange these relationships thinking that they represent valid relationship, but they may not be so. Such correlations may not predict the future. They might give us statistically incorrect, irrelevant trends which may not be helpful for us. So this is called the data mining bias. Next is the sample selection bias. Bias basically means we tend to exclude a certain section of population and prefer a particular section of the population. So going this way in selecting samples means that you are being biased in sample selection. Then next one is the survivorship bias. Survivorship bias, let's say this is the population. You exclude certain information because certain entities in the population, they do not exist. Why? Because they were poorly performing. Thereby the remaining population contains only those firms and entities which are profitable. So which are surviving. They are gone, dead, finished, wound up, liquidated, and they are surviving. So basically you are just selecting from those firms' returns that exist. Those that have been kicked out, they are excluded. So only the firms that are surviving are considered during sampling. This is survivorship bias because your bias, even inadvertently, is towards those firms that are surviving. That's what you call the survivorship bias. Then we have look ahead bias. Sometimes we as analysts, we use certain numbers which are not presently available. Like there would be a question down the line. We want to calculate the price earning ratio, right? Price is readily available at the end of the year, 31st of December 2021, right? At the end of the year, you have this price available on the stock market quoted price. But unfortunately, the earning number, EPS, which is calculated under the IAS 33 standardized EPS calculation, it's governed through an accounting standard in the IFRS as well as US GAAP. But this EPS number would be available maybe after 2 or 3 months from the close of the year, because it takes time before the financial statements are finalized, audited, and then they are published and then dispatched or sent to the shareholders. So that's the problem. So if an analyst is trying to calculate PE, he might use this number at the end of the balance sheet. But this number he might use from the previous 3 quarters and put it there. Now this is what you call the look ahead bias. He has used earnings which are not yet available with the numbers with the price that is currently available. Right? So this is look ahead bias. You are using an estimated earning which may not be true when the results are published. Right? Then next is the time period bias. This clearly involves seasonality. Certain firms, seasonal in nature, they have some higher earnings in certain season and not in others. So when we are comparing quarterly numbers, so these comparison can mislead because certain firms are influenced by seasonality. All right, so that ends your reading. Now we have some good quality questions that will further enhance our understanding. All right. Which of the following is least likely a property of student's t distribution? Least likely. Mind the word, this is the one that is twisting the question. All right. As the degree of freedom gets larger, the variance approaches 0. This is incorrect. As the degree of freedom gets larger, the distribution approaches to a normal distribution. The difference between the t distribution and the normal distribution is that the normal distribution has fatter tails. Let me take you back exactly where you need to. Now this one is the t distribution where the degree of freedom is 1. When degree of freedom goes to 4, see the fatter tail tends to be narrowed down now. These are the fatter tails now narrowed down. When the degree of freedom reaches 15, and you can see further the tails are becoming even narrower. So as the degree of freedom increases, gets larger, a t distribution approaches to a normal distribution. That's the right conclusion. So as the degree of freedom gets larger, the variance approaches to 0. This is wrong. In fact, as the degree of freedom gets larger, the t distribution approaches to the normal distribution. This is basically incorrect. Then it means B and C, they must be correct. It is defined by single parameter. Yes, the degree of freedom which is equal to n minus 1. Correct. This is a correct statement. It has more probability in its tails because the tails are fatter and less at the peak than the standard normal distribution. Perfect. This is exactly what we saw a little while ago. All right, here we go. A random sample of 100 computer stores spent an average of $75 at the store, assuming the distribution is normal and the population standard deviation is 20. The 95% confidence interval for the population is closest to. Now we know what to do. We know what to do. Mean plus minus, since alpha here is 5%, so you're talking about alpha by 2, that is 2.5%, or simply alpha by 2, multiplied by the standard error. And what is standard error? Ideally, the population standard deviation upon the square root of the sample size. So we have the numbers, we just need to plug them in. 75 is your average statistic, sample statistic. And since we're talking about 95% of degree of confidence, 5% is the level of significance. And I'm sure you know that at this point, 1.96 is the value. Multiplied by 20 is the population standard deviation, and the sample size is 100, so that will give you a denominator of 100 square, which would be 10. So when you will simplify this, it's going to be 75 plus minus 3.92, which means it's going to be 78.92 and a 71.08. So your true population parameter falls within this range. We are 95% confident, right? So that makes A to be the correct option, right? A it is. All right, the next question will involve the use of t distribution. Why? But let us see first. Best Computers Incorporated sells computers and computer parts by mail. A sample of 25 recent orders. That tells me n is less than 30. That's the first indication that we need to go for t distribution. The mean time taken to ship out these orders was 70 hours with the sample standard deviation 14. Now this is another indication that our standard deviation of the sample is given, not the population. It has to be then the t distribution. Assuming the population is normally distributed, of course t is also normally distributed, the 99% confidence interval for the population mean is, we know what to do. We have the point estimator, plus minus this time t, alpha by 2, alpha here is 1% level of significance. So alpha by 2, that is 0.05, whatever they want to do, just write alpha by 2, and multiplied by the standard error, that is s upon square root of n. So we have the mean here, mean was 70. plus minus. Let's look this up here. We need 1 upon 2, that is 0.5%, but when you convert it to, it will be 0.005. So we need to look down this column at 24, why 24? Because the sample size is 25, and the degree of freedom is n minus 1, so 25 minus 1 is 24, right? So it's going to be 24 at the point is 2.797. 2.797. 2.797 times the standard deviation of the mean, that is 14, divided by the square root of 25, sample size. If you solve this all, what you get is 70, and this solution would give you, as you can see, 7.83. So this is, we don't need to solve further. C is your answer, right? C it is. Next, what is the most appropriate test statistic for the construction of confidence interval for the population mean when the population is normally distributed but the variance is unknown? See, when the variance, let us go back to that summary table. So we have unknown variance, right? For unknown variance, whether the sample size is less than 30 or more than 30, we go for t statistics, right? But if the sample size is bigger, we can use the z statistic as well. Since we are not sure about the sample size isn't given, the question is silent on sample size, then it could be t statistics or z. Let us see. So in this question, the population variance is unknown. Normally z statistic should be used since we do not have the sample size, whether n is greater than or equal to 30 or it's less than 30. So it is most appropriate that you go for Alright, so as you saw a little while ago, since we do not have the population standard deviation, right, and our sample size is not available, so it could either be t or z. Look at the options given. Let us see the options, what they say. The z statistic at alpha with n degree of freedom. This is a ridiculous option because in z statistics we do not have degree of freedom. Z table doesn't require any degree of freedom. That is only applicable in t statistic or t distribution. B, the t statistic at alpha by 2, n degrees of freedom, wrong. There are no n degree of freedom. There are rather n minus 1 degree of freedom. So out of these, C is the most appropriate. The t statistic, why? Because the standard deviation of population is not available, and n minus degree of freedom. So that makes C to be the correct option. Without doubt, C is our right answer. All right, next, when constructing a confidence interval for the population mean of a non-normal distribution, mind the word non-normal, right? When the population variance is unknown, the population variance is also unknown. The non-normal distribution, and the sample size is larger than 30. An analyst may do what? Now let us go back to the table so that we are sure what we are doing. So when the sample size is greater than 30, you have two options: non-normal distribution Z statistic with known variance, known population variance, non-normal distribution with unknown population variance. In that case, we have t statistic. But here we have unknown variance. So it means we are most likely at this position. Non-normal distribution, yes. Unknown variance, yes. Then it's t statistic, ideally. But Here the z statistic is theoretically acceptable here. So it means t and z are both possible when non-normal distribution with unknown variance involved and the sample size is greater than 30. So as per the table, either z statistics or t both are possible because the sample size is large. So we are sure now it's A. Question number 6. Jenny Fox evaluates managers who have a cross-sectional population standard deviation of returns 8%. Okay. If the returns are independent across managers, how large a sample n does Fox need so that the standard error of sample mean is 1.265%? Now this is a question in the total reverse order. So far we have been calculating the standard error, but here the standard error is given. We have to work back, so it's no big deal. Standard error is equal to population standard deviation, right? If not given, then we may take the sample standard. We have been given the population standard deviation, so that's 8 upon n. That's what we need to find out. So standard error has been given 1.265. Let's keep the percentage sign here, and we have been given the population standard deviation, that is 8% upon n in the square root. So what you need basically is take n on the other side and write 8% upon 1.265%. Take the square to get n, and when you do, your result would be approximately 40. That's fairly straightforward maths. 40 is your result. All right, next. The annual returns on small stock have a population mean of 12% and a population standard deviation of 20%. If the return are normally distributed, a 90% confidence interval on mean return over 5 years period. Now this is interesting. N is 5, just 5. Right? Now the question is, since n is 5, which is less than 30? Remember, if n is greater than equal to 30 or less than 30, as long as the population is normally distributed and you have the population standard deviation, go for z distribution. That's what we learned a little while ago. So we need to find the confidence interval. For that we need the point estimate plus minus here z alpha by 2 times the standard error. Let us plug in the numbers. The mean here is 12 plus minus, since we're talking about the 90% confidence interval, the level of significance 10%, 10 by 2 is 5, so you're talking about z 5%, and if you're 10 level of confidence interval means we're talking about 1.65 times standard deviation from the mean multiplied by the standard error, which can be calculated by dividing the standard deviation of the population with the square root of the sample size. So if you do and compute all this, which you know what to do, it will be, I think, 8.94%. And a simplification would give you a negative this one is basically 8.94%. times 1.65. So it means you will have a larger negative number. So it means negative 2.75% to 26.75. We've done many questions like these. So it means we're 90% sure that our true population parameter will fall within this range. And that is B. An analyst who uses historical data that was not publicly available at the time period being studied will have a sample with what? Now this is specifically what we discussed a little while ago. You are using historical data that was not publicly available at the time period being studied. Most probably is price earning ratio. Price is easily available at the end of the day, whichever day of the year it is, if the markets are running, divided by earning per share. And this is dependent upon the closure of financial statement. We won't know it beforehand. Right. So in this case, the analyst here is looking ahead. This is called look ahead bias, right? Because normally the financial statements are made available at least 3 months, 2 to 3 months. It takes audit and then finalization and then a lot of activities involved. So this is clearly look-ahead bias. You can relate this question with what we discussed there in look-ahead bias with the example of price-earning ratio. All right, then we have A. Which of the following is most closely associated with the survivorship bias? What is survivorship bias? Remember, we exclude those firms that do not exist over time. They have been kicked out of the market because of the bad performance. So what you have are the firms that are good, and you use those good firms to calculate your test statistic. So this would mean that it is focusing on survivorship bias. So price to book ratio, this would mean it is look ahead bias. This is the one we're talking about. Mutual fund performance studies, certain mutual funds may have closed over the period. So you're just taking those that surviving. So this is what will result in survivorship bias. So gentlemen, that gives C to be the correct option, and that also ends your reading.